Alright, hello class. Okay, so we're going to continue talking about radiation. So I mentioned, we've got the basic law over here, the rate that energy is being radiated away. So let's say we have an object and it's radiating energy. And so we might expect this object, it's losing energy, so you might expect this object to cool off. But of course, that doesn't happen. If you have, say, a glass of water and you set it down, it's radiating energy away constantly, so why isn't it cooling off? And the answer, of course, is that it's absorbing energy from the environment as well. So this would be the power radiated. And then it also absorbs energy from the room through either conduction or radiation, either way. So there's power going in from the room. And when an object is in equilibrium, these two are equal to each other. So say you have an object at room temperature and you just leave it there, it remains at room temperature. So what that tells you, it's absorbing energy the same rate that it's radiating energy. So this is a power radiated, that's also the power absorbed. And here, so we've got power radiated, power absorbed. Let's say in equilibrium, these are equal to each other. So in equilibrium, the power that, I'm going to write it the other way, the power that it absorbs from its environment is equal to the power that it is radiating. Now the power that it's radiating depends on the temperature. But let's say something's in equilibrium at room temperature. If you change the temperature of the object, that's not going to affect what it's absorbing from its environment. So the power absorbed, this would be the power that it's radiating at the, we can just call it room temperature. So say we have an object, or say the room temperature is, say, 30 degrees Celsius, and say this object is at 90 degrees Celsius. Now, we know that the power that it radiates would be E sigma A times the temperature of the object itself. Now, we have to convert this to Kelvin. It's 273, that's the offset. So this would be 363 Kelvin. So this is the rate that energy is radiating from this object. However, what it's absorbing would be E sigma A times 303 Kelvin to the fourth. We use room temperature. Because if this object was at room temperature, it would be in equilibrium, so it'd have to absorb at the, at this temperature. And so the net power radiated, power net radiated would be, power radiated minus the power absorbed. All right. So yeah, just this observation that the rate that something is absorbing energy depends on the temperature of the room, whatever its surroundings are. Another interesting thing is the power absorbed from the room. We could say this is E sigma A times room temperature to the 4th power. But another factor besides the temperature is the emissivity. So let's say we have two objects. Say we have a block of aluminum and a lump of coal. So here, aluminum and which one is radiating more energy? Now, say they're both at room temperature. Both at room temperature. So which of these two objects is radiating more energy? Now, I think, if you just ask people randomly, they'd probably say aluminum because it's shiny. You think it's giving off radiation. But actually the coal is radiating more energy because its emissivity is higher. So it absorbs more energy from its environment, which means it radiates more as well. So it can remain in equilibrium. So objects that are good at absorbing energy are also good at radiating energy. And something like aluminum is very bad at radiating energy. It doesn't radiate nearly as much as something like coal. So maybe a kind of surprising result there. Not very intuitive. All right, so got one more example I want to look at, and that'll be it for radiation. So now I'm going to read this problem. It says, a wood-burning stove is being used to heat a room. The stove is being kept at a constant temperature. So here's our stove of, I'll just say 471 Kelvin. So it was 198 Celsius, so that'd be 471 Kelvin. Again, it's easy to convert the two. The hard part maybe is just remembering to do so. Okay, the room is kept at a constant 29 Celsius or 302 Kelvin. Promise I will clean this board before the next video. It's getting hard to read. The stove has an emissivity of 0.9 and an area of 3.5 meters squared. What is the net power radiated by the stove? So again, pretty straightforward now that we've talked about the background, but it's radiating according to its temperature. So we'd have E sigma A times the temperature of the stove to the 4th power, but it's absorbing, using the same formula just at room temperature. So again, these factors, we can just, I'll write it out the long way. I guess this picture was kind of unnecessary. So the net power so that's what it's radiating according to its temperature, and what it's absorbing from the environment depends on room temperature. And again, we can factor out the E sigma A, and then we have Ts to the 4th minus Tr to the 4th. So again, if we just plug in the numbers, this is 0.9. I'll just write it as a fraction. And then A is 3.5 meters squared. Sorry, I forgot sigma. 5.67. And again, it's 10 to the negative 8, so I'm going to put that on the bottom. And then we have 471 to the fourth minus 302 to the fourth. That'd be Kelvin to the fourth. So again, the units are going to work out very simply. Here we have meters squared cancel. So we get a power in watts. And if we plug in the numbers, the net power that it's radiating is 7.3 kilowatts. So again, it's a positive number because it's warmer than the room. So it's radiating more than it's absorbing. And again, that would cause it to cool off, but you've got a fire inside that's burning it to keep it warm. Okay, so again, the black body radiation. My battery ran out earlier, so I had to break it up into two pieces. So there wasn't that much to finish here. But, yeah, that's it for this video then.